We considered hygrothermal relations for a unidirectional lamina, and we are going to extend this representation for an angle lamina, as shown here. This is the angle lamina. Global axes are x and y, and now local axis, principal axis of orthotropy are 1 and 2. Angle of inclination is theta for the fibers, and how can I write the strain relations for such a configuration? We are going to start with transformation representation. Total strains, epsilon x, epsilon y, and gamma xy. These are global strains, and I can write these in terms of local strains by considering transformation formula. If you recall one of these formulas I've shown, it was in this form: epsilon global equals R times T inverse times R inverse times the local strain matrix vector epsilon 1, epsilon 2, gamma 1, 2. Now, as you know, R is the Rorschach matrix and T is the transformation matrix. Each is a total strain, and we know how to express this total strain in the principal coordinate system. It was given in the previous representation: epsilon equals S times sigma plus epsilon T plus epsilon C. It's written here. And substituted into this result, that's going to give you epsilon x, epsilon y, gamma xy. This is equivalent to R T inverse, R inverse, times this local strain vector, but we are going to express it as S times sigma 1, sigma 2, tau 1, 2, plus thermal strain vector epsilon 1 T, epsilon 2 T 0, plus hygroscopic strain vector epsilon 1 C, epsilon 2 C, and 0. It's substituted into this result, and we can consider further modifications on this equation. First of all, this local stress can be written in terms of global stresses. That is, this stress vector, sigma 1, sigma 2, tau 1, 2. We know that this is equivalent to T times global stress sigma x, sigma y, tau xy. And substituting into the above, result, you'll get epsilon x, epsilon y, gamma xy. This is equal to S bar times sigma x, sigma y, tau xy, plus this term. Well, I'm going to write it in a more compact form. The second term is going to be epsilon xt, epsilon yt, gamma xyt. And the third one is epsilon xc, epsilon yc, gamma xyc. These are found. The definition of S bar is known. S bar here is due to this product of T inverse R inverse S times T. That is S bar, where we know there's transformed compliance matrix S bar. It's equal to R T inverse R inverse ST. And the other terms, this term, thermal strain vector epsilon xt, epsilon yt, gamma xyt. This results from this multiplication of T inverse R inverse times local strain vector, that multiplication. Therefore, this is equivalent to R T inverse R inverse times epsilon 1t, epsilon 2t, 0. And a similar term here for the hygroscopic strains. The vector is epsilon xc, epsilon yc, and gamma xyc. And that's equivalent to R T inverse R inverse times epsilon 1c, epsilon 2c, and 0. Various matrix modifications, but this is the basic result in the global coordinate system. Such a representation is applicable. This is the total strain in the global coordinate system. That is mechanical strain, thermal, and hygroscopic. Each term is derived in the global coordinate system, but we can simplify these thermal strain expression and hygroscopic strain expression further. They are defined here. This is the thermal strain, RT inverse R inverse times epsilon global, and hygroscopic strain, again, RT inverse R inverse times epsilon hygroscopic local, but carry out this multiplications by MATLAB or Maple, simplify the results, and you will end up with compact representations for these strains. Again, these terms are simplified further. Thermal strain from xt, epsilon yt, and gamma xyt. When we carry out that multiplication and simplify the result, we can express this as delta t times alpha x, alpha y, alpha xy. And a similar way, epsilon xc, epsilon yc, gamma xyc. Delta c times beta x, beta y, beta xy. These are thermal expansion coefficients and moisture expansion coefficients in the global system. And the expressions of these thermal expansion and moisture expansion coefficients can also be found, or they are found as a result of matrix multiplication. Alpha x, for example, is c squared alpha 1 plus s squared alpha 2. Alpha y is s squared alpha 1 plus c squared alpha 2. And alpha xy is 2sc times alpha 1 minus alpha 2. These are thermal expansion coefficients in the global system. Alpha x, alpha y, and alpha xy. Thermal expansion coefficients in the global coordinate system. C is cosine theta, S is sine theta. We are following our usual notation. And analogous relations for moisture expansion coefficients, beta x is c squared beta 1 plus s squared beta 2, beta y is s squared beta 1 plus c squared beta 2, and beta xy again 2sc beta 1 minus beta 2. Alpha 1 and alpha 2 are thermal expansion coefficients in the local system. In the global system, in addition to alpha x and alpha y, there is alpha xy, which means that there is a thermal shear strain, and this is gamma xyt. The thermal shear strain occurs in the angle lamina because the principal axes are 1 and 2, and now we have a fully populated matrix, the compliance matrix, and thermal shear strain terms, gamma x, y, t, and the thermal hygroscopic strain term, gamma x, y, c. They are not zero. Thermal expansion coefficient form and moisture expansion coefficient form is thermal strains are also defined. But that's the final result. Again, we can calculate either total strains or stresses by making use of these relations. If delta T and delta C are given, you can evaluate total strain in an angle lamina by such a relation. Any questions about these results? I'll also give a numerical example that shows the application of these equations. Example. Find the following. For a 60-degree or let's emphasize that for a free 60-degree angle lamina of glass epoxy first coefficients of thermal expansion or thermal expansion. Part 2, find coefficients of moisture expansion. Part 3, total strains if delta T is minus 100 degrees Celsius and delta C is 0.02. These are given. First, coefficients of thermal expansion, and this is an angle lamina. Keep in mind that which is shown here, but let's copy this. This is the angle lamina. I would like to find these coefficients in the global system, alpha x, for example, c squared alpha 1 plus s squared alpha 2, is that right? Alpha y and alpha x, or I'm going to copy all these results. They are already written. And for part 1, these results alpha x, alpha y, and alpha xy. C and S are known. The angle is given as 60 degrees. And how can I find alpha 1 and alpha 2 values?
From table 2.1 hocam.
Yes, table 2.1. If you look up this table, you'll find alpha 1 as 8.6 10 to the minus 6 1/degree Celsius for this glass epoxy composite. Alpha 2 22.1 10 to the minus 6 1/degree Celsius. These are known. But everything is known, therefore alpha x is 1.873 times 10 to the minus 5 1/degree Celsius. Alpha y 1.198 10 to the minus 5 1/degree Celsius, and alpha xy. This is negative, minus 1.169 10 to the minus 5 1/degree Celsius. Coefficients of thermal expansion in the global coordinate system are found. And what are the coefficients of moisture expansion in the global coordinate system? I will directly give the results again from table 2.1. Find beta 1 as 0. It means that it's insensitive to the variations in the moisture content, and insensitive in one direction. Hygroscopic strain in one direction will be 0. However, in two directions, it is sensitive because of the polymeric material at 0.6. And plug these in the formula to calculate beta x. This is 0.45. Beta y is 0.15. And beta xy is minus 0.52. These are coefficients of moisture expansion. They are calculated in the global system. And finally, the total strains, if delta T is minus 100 degrees Celsius and delta C is 0.02, we can refer to the general representation of total strain. And let's copy this one more time. This is the general representation in the global system. Part 2. We ask the total strain this vector can be calculated. It's a free lamina. Now, what can I say about the stress vector? For stress vector for this free lamina under uniform temperature and moisture content changes. What is stress in a free lamina? This is, it's freely expanding. Therefore, there are no mechanical strain terms. This term is 0. And for this reason, total strain epsilon x, epsilon y, gamma xy is thermal strain vector delta t times alpha x, alpha y, alpha xy plus delta c, beta x, beta y, beta xy. And this total strain is delta t, and the difference between total strain and hygrothermal strain is 0, and there are no stresses. And this can be computed because we know the coefficient of thermal expansion vector. We know this vector delta t is given, and delta t is also known. And I'm going to write down the final result. So x, epsilon y, gamma xy, the numerical values 7.128 times, let's write it separately, 1.803 minus 9.223 multiplied by 10 to minus 3. And these are the total strains, or which is equivalent to the hygrothermal strain vector. Any questions about these results? These results? Any other questions or comments? A fixed plate. An angle plate, but an angle lamina, but still there is a change in delta T and delta C. So how would you solve this problem? So which quantities are to be computed for such a problem?
Actually, all the parameters, including mechanical, thermal, and hydro. I couldn't say it. Moisture.
Yes, you can calculate hygrothermal strains, that's right. But now you have to find stresses in this case. Stress terms. These are not 0. And how can I calculate stresses? In the previous case, stresses were 0, now they are not 0. And equate totals changed. Now, total states are 0 to find stress. And this could be a good homework problem or an exam problem. Any other questions about this part? I'll stop recording if you don't have any questions.